Hey everyone, this is Shadia Nogabi from Microsoft Research, and today I'll be presenting our work, Redesigning Data Centers for Renewable Energy. This is a joint collaboration with Microsoft, CMU, and UIUC. As everyone knows, cloud computing has become an increasingly popular concept, so much so that it has become a substantial source of carbon emission. Almost 3.7% of the global emission is coming from the cloud, and this is only becoming worse with the emergence of compute-heavy workloads such as machine learning and deep learning. Because of this, all major cloud providers have pledged to become carbon zero or negative in the near future. And renewables are key to reaching this vision. Renewables have had significant progress, so much so that they are even cheaper than traditional energy sources. However, renewables are highly variable energy sources. There are many sources for this variation, like diurnal patterns in solar production day and night, seasonal changes, or weather conditions. On the right-hand side here, you can see the power generation of two main sources, solar and wind, over a 5-day period. And as shown, both of them have steep increases and decreases very frequently. And the question is, how can we have reliable computing on such variable power supply sources? So the traditional way of doing this is to move power or energy across space or time to reach the computation demand. For space, we have transmission lines which aggregate energy across multiple sources, some which are even non-renewable, and move that energy to a centralized location like a data center. But the problem with transmission lines is that they have high cost. Often like half of the cost of energy is because of the transmission, and they're very slow to deploy in new locations. On the other hand, they're also an opaque mix of renewable and non-renewable, and the end user has no control over that. They cannot request to be more clean or green from the grid. An alternative option is to shift across time using batteries, where they store the energy and use it at a later time. But the problem with batteries is that they are at a very small scale. Currently in the US, the total battery capacity is only 0.4% of the overall renewable production. We propose a paradigm shift where instead of having these big data centers, we move them across to where the renewable generation sites are and size them accordingly to the power generation of each individual site. And then, instead of moving energy to meet computation demand, we shift the computation demand to meet the availability of energy. So as there is more power produced, we power up more servers, and if the power production drops, we power down certain servers. We call this a virtual battery since, similar to how batteries avoid transmission lines by shifting energy over time, the virtual battery also avoids transmission lines, but it does this by shifting computation. In reality and in practice, we expect to have a combination of such virtual battery sites alongside these traditional data centers around. But now this virtual battery causes an availability challenge because applications can lose their resources drastically and frequently. So there are two types of applications. There are degradable applications, which are applications that know how to cope with frequent resource losses, like spot instances or harvest VMs in the cloud. And while these are a great fit for such an environment, they are not high-paying applications and the most profitable. On the other hand, we have these high availability applications which require certain level of availability guarantees similar to the on-demand VMs, and these are the most profitable VMs. And in this work, we're looking at how can we maximize the support for such high availability applications and use the remaining amount of energy for degradable applications. We looked at the energy production of different sites, and we observed that there is a complementary pattern across different locations and energy sources. Here on the right, you can see the energy production of a solar farm in Norway. And while there are many times that it goes down to zero, which would be unacceptable for an app requiring high availability, if we only combine the energy of another nearby site, a wind farm in UK, we can have a constant amount of energy throughout that window, which we call this stable energy. And then if you just combine one more site, you can see the variability reduces significantly and the stable energy increases at the same time. So yes, we can use multiple sites to help with variability, but this introduces a new networking challenge. Now, applications that could run in a single data center with high availability have to run across multiple sites to reach availability. And while there are well-known techniques of replication and migration for cross-site applications, the scale of the network overhead is much higher. We analyzed this by simulating a virtual battery site with 700 servers and used a public trace of power generation of a single site. And we measured the amount of data migration that needs to happen based on a VM arrival trace in our production clusters in Azure and a VM allocation policy based on Azure. So what happens whenever energy drops? We first unallocate cores, and if needed, we will move applications. And then whenever energy increases, we bring back applications and we count them as in migration. So as shown, with minor variations, they're completely absorbed by just shutting down unallocated cores. But when there are sudden increases, which we saw like in 20% of the power variation cases, these can cause multiple terabytes of data migration. And while these migrations are spiky, we also observe they're predictable. So bulk of the migrations happen when there are sharp changes in power, which can be predicted very accurately for the near future. Here on the right, you can see the power prediction for two sources, solar and wind, over different intervals. And as shown, for like a 3 hour ahead and a day ahead, there is very good accuracy on predicting the exact power generation. And this brings up to the main question we're trying to solve, which is how can we schedule applications across these highly variable but predictable resources in a way that we can ensure high availability, have low and non-bursty network overheads, and minimize the overall energy usage. So we solve this in a 4-step process. First, we generate an overall graph of the virtual battery sites, where two sites are connected if they have low latency connections between them. Then from that, we find subgraphs of virtual batteries which are complementary to each other. And then for any application that comes in, or whenever there are sharp changes, we pick a subgraph and a site or a few sites to place that application. And finally, we decide exactly how to allocate the VMs of that application across the chosen sites. For the last 2 steps of this process, we have developed a prototype scheduler, which uses 3 main insights. First, it places apps where there is the power is predicted to retain or increase. Secondly, it tries to maintain a good mix of degradable apps and high availability apps so that they can absorb a lot of the variations. And then finally, it tries to preemptively migrate workloads to reduce the peak network overhead. We formulate this problem as a mixed integer problem with 2 objectives. First is to reduce the overall migration overhead, the total migration overhead, and then secondly to reduce the peak migration overhead, and have 2 variants of it. One is MIP, which only optimizes the total migration, and MIP peak, which optimizes both objectives. We evaluate our system using a 4 virtual battery cluster setup and use the public power traces from the ELIA dataset and the Azure VM arrival traces, and compare the 2 variants of our MIP with a greedy-based approach which places applications where there is the best amount of energy available at that time. As shown in this table, both MIP variants can significantly improve the total migration, almost 30% less, and then the MIP peak additionally improves the peak migration by 4.3x. In conclusion, we propose virtual battery, a paradigm shift where we shift computation to meet the energy demand. And by doing so, we can have sustainable computing using only renewable sources. This approach also opens new revenue opportunities like edge computing at virtual battery sites, or co-locating them with satellite ground stations, or even participating more effectively in energy markets. Thank you for your time. I can take any questions now.